Okay. We're good. Okay, nice to see you guys. Sorry, disorganized as always here. Right, so let's see, in terms of course announcements and all that boring stuff, you've got another homework to do. It's due, what, a week from Thursday, is that right? Yeah, so you might consider doing your homework. Really, I would suggest you leave yourself ample time for coding and stuff and making sure that you're not rushing this one to the last minute. And a few of you have figured out that if you come to office hours, we will gladly just work through it with you. For those of you who aren't, you're suffering alone for no real reason, but that's on you. Another reminder you might have seen on Piazza, apparently Chris has to leave out town this week, so we won't be able to have section on Friday, but that'll continue next week. Any questions on the organizational front? Cool, I think it's a pretty ordinary week. Right, so today we're going to continue our discussion of eigenvalues and eigenvectors, which is one of my favorite topics and a very central one in numerical analysis. So hopefully from our last lecture, what I convinced you is that computing eigenvectors isn't just a fun mathematical exercise that they do to torture you in college linear algebra class, but actually there's a lot of totally reasonable optimization problems out there in the universe that justify computing eigenvalues, right? And we saw quite a few of them. If you recall, some of the basic problems that we looked at were things like minimize 1/2 x transpose ax subject to the norm of x equals 1, or maybe finding a basis constructed out of the eigenvectors of A turned out to be a nice way to invert matrices and solve ODEs and so on. Right? So essentially, hopefully, the point that we're at now is that at the very least, we can see why people want to solve these problems. So our next task is going to be, as usual, we keep following the same pattern in this class, right? So we motivate the problem. Now we got to make sure that the problem makes sense to solve, right? Like when do matrices have eigenvalues? Then we're going to solve them, and then we're going to go back and talk about conditioning, right? So that's an ambitious plan for today. We'll see how far we get, and we'll finish it off on Thursday, and we'll also start the SVD, which is the final matrix factorization in this class. I think. I have to think about that. It's certainly the sort of last of the major classical ones to cover. Okay, so once again, so clearly it makes sense to seek eigenvectors, and many of the problems that we covered in the previous lecture would be facilitated by computing them. But now we got to ask, when is our problem well posed? Like, for example, if I just hand you some arbitrary matrix out there in the universe, do I even know that it has an eigenvalue and an eigenvector? So does it make sense to begin with, to search for such an object? Right? And so that's where we're going to start today. We're not going to prove too many of these properties in class because I think this is really, hopefully, something your linear algebra professor did. But I thought I'd kind of recall a few basic facts just so that we're all on the same page and agree that this problem is well posed. Okay? So most likely what we'll do is verify a few of these facts. I'll get myself confused with the theory and indexes and notation, and then I'll say that it's trivial and you should have covered it in linear algebra anyway, and we'll skip the rest. Does that sound good? Fantastic. So the first question we might answer is can we ever expect to find an eigenvector? So for example, are there matrices A for which there exists no x with ax equals lambda x? But at least to me, it's not obvious, right? It could be that there's some matrix out there that has no eigenvector at all. As you can see stated in this lemma here, there does exist an eigenvector, but it might have a complex eigenvalue or complex entries. Okay? So for fun, any of us have seen this proof before. I remember how to do this one. There are actually a bunch of different proofs of this. I thought that there are some really clever ones out there. So I'll outline my favorite one. Notice today I've got lots of notes because these are the kinds of things that are really easy to get wrong. Okay, so what we're going to do is we're going to assume that A is not equal to 0. Notice, by the way, that if A equals 0, it's pretty clear that A has an eigenvector. Can anybody give me an eigenvector of A? Literally any vector. Actually, 0 is the one thing that isn't an eigenvector of A, right? Because we define eigenvectors to be non-zero. But literally anything else, if you multiply it by A, you get 0 times that thing. So it's totally fine. Okay, so here's going to be kind of a sneaky trick. By the way, I lifted this proof from this book titled Linear Algebra Without Determinants. Have you guys seen this? It's a clever, I think this book is fantastic. There's this, This is Axler, and it has this little logo. It has like that, which I thought was really cute. But actually, a lot of his proofs, I think, actually are much more intuitive than with determinants, which are kind of a nice mathematical shortcut, but actually justifying why they're intuitive objects to work with is kind of a hard thing to do. And by the way, computing determinants isn't even numerically such a good idea. Okay, so anyway, now, sorry, I put a little implied zero there, but I got ahead of myself. Take any x not equal to 0, and now we can do a kind of funny thing. So we're going to construct the following set, which is x, ax, a squared x, a to the nx. Cool? So, quick reality check here. How many elements are in this set? N plus 1, and A is n by n. So in particular, this set has to be linearly dependent. Right? There's n plus 1 vectors in Rn, right? So that means that there exist Ci not all 0 subject to such that 0 is equal to the sum Ck a to the kx, where k goes from 0 to n. Does that make sense? That's sort of the definition of linear dependence, right? That there's sort of a redundancy. I can add up all the vectors and get 0 with some non-zero coefficient. Okay. So there's a lot of different ways that you can prove this little theoretical result, and they all build on like heavy results from some corner of math or another. The one that we're going to use builds on a heavy result you might have seen in algebra class, which is, remember that you can factor any polynomial in the complex numbers? And so that's the fact we're going to use. This is the fundamental theorem of algebra. And it's actually not obvious from what we've done so far how we're going to apply it. So here's how we're going to do it. Define the following polynomial. So this is f of z, and it's going to be equal to c0 plus c1z plus c2z squared plus cn z to the n. Okay, so this is a function that inputs a complex number and outputs another complex number. And the coefficients just happen to be borrowed from this expression up here. Cool? We can define anything we want. I'm just defining this weird object here. By the way, this is also suggestive of an algorithm for computing eigenvalues. I've never tried it myself. I think it's probably terrible. Okay, but in any event, what do we know about the fundamental theorem of algebra? You guys remember what this one says? Oh, man. Yeah, but in particular, it actually doesn't even matter how many roots in this case. It's just that this thing has roots, that I can always factor that there exists greater than or equal to 1 roots that we'll call zi. These are complex roots, right? We don't know that they're real valued. And some c not equal to 0. In fact, c is going to end up being c to cn here, I think. No, I'm sorry, that was wrong. If cn is 0, then you have to be careful. So that we can write the following, which is f of z. I think this is a thing you all did in algebra class, but you might have forgotten that it's always possible. Which is equal to c times z minus z1, z minus z2, z minus zn. Right, so this is just factoring our polynomial in terms of its roots. Just, I say, but like the fundamental theorem of algebra says you can always do this. You should be a little careful with m, right? That m might not be equal to n in the case where cn is equal to 0. Everybody with me so far? Chris looks suspicious.
This is not actually a theorem in algebra, right?
This is literally the fundamental theorem of algebra.
I know.
See, I wrote it on the board.
But the proof is like inherently analysis-based.
No.
You're saying that this function is a root, so you need to make some like analysis assumption.
I'm going to let you Wikipedia that one. Okay. All right, but one way or the other, even if we have to apply a little bit of calculus, which I don't think we do, we're pretty sure that we can find roots. In other words, what the complex numbers are complete, I guess. Okay, algebraically complete, that is. Right? Otherwise, you would have trouble. What is it? You can't trisect an angle, all that kind of stuff. There's all these theorems all kind of fall in the same pile. Okay, so here's a kind of sneaky thing that we can do, which is the following. We're going to copy our expression from before. So what do we know? We know that 0 is equal to this particular linear combination of vectors now, right? So I'm going to write it, I'm going to expand that sum. So in particular, it is C0x plus C1ax plus Cn a to the n x. Cool? And now I'm going to factor out as follows. I'm going to say this is C0 times the identity plus C1a plus dot 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 plus Cn a to the n x, like that. And here's a really sneaky thing that we can do. So we have this equality between functions f, right? We have two different forms for f. You can very easily convince yourself that because of that, we can actually write the following. This is equal to c times a minus z1 times the identity, a minus z2 the identity. Times x. And this follows directly from the equality up here, even though I happen to put an a instead of where there was a z before. If you expand out this product, you'll see the coefficients are exactly the same. Okay. So, what are we going to do? How can we conclude now that there exists an eigenvalue? I claim we're actually pretty much done. This is a really slick proof. So, we have that a big product of matrices times x is equal to 0. Moreover, we know that x is not equal to 0, just by definition, right? So we have two cases. Either this big product of matrices is invertible or it ain't. Okay? So, what happens if this product is invertible? So I multiply both sides by the inverse, and what I'm left with is x equals 0. But that's a contradiction. Yeah? So in particular, we know this giant product cannot be invertible. At least one of these matrices must be singular. That make sense? Everybody following? We agreeable? Okay. So there exists an I such that A minus ZI, has a null space. Right? Because otherwise this whole thing would be invertible and x would be 0, but we know that can't be the case. That make sense? Okay. So because it has a null space, we know that there's some a minus zi, times the identity, times some vector is equal to 0. But notice that is exactly the same as a v equals zi v. Yeah? So we're good. Yeah? At least for the very first vector where you got 0. Right? After that, you're multiplying a bunch of zeros. Any questions about that proof? Isn't that slick? I think this is a really clever little proof of this fact. Now, the thing that I don't know is, like, if I'd proven this lemma some other way, could I get back to the fundamental theorem of algebra? That one I'd have to think about. Possibly. I don't know. Okay. Right. So in any event, the good news is that our eigenvalue problem is well posed, right? You see that that's essentially what we just showed. That, like, at the very least, we can always write algorithms for looking for at least one eigenvalue, even when the A is not symmetric, and we can possibly find it. Yeah? It's not like our search is in vain. Moreover, a different lemma, which I think maybe we'll skip because, like, enough already, is just more of the same kind of stuff, is that if you have distinct eigenvalues, the eigenvectors must be linearly independent, which kind of feels intuitively correct. So in other words, you can't, like, somehow combine the eigenvectors with, like, lambda equals 3 and get an eigenvector with lambda equals 5. That feels wrong, right? But I'll let you guys reference in the book for a formal proof of that. Is that okay? I can do it if you don't trust me. I have it here. I wrote it down. The enthusiasm. Okay. So if we combine all of these different facts together, what you can conclude is that there's at least one eigenvector and there's at most n eigenvectors, right? Because if you have more than n, then somehow you're violating this linear independence condition here. So now the name of the game is a little more well-defined. Okay? All right, but in general, matrices do not have to have a full set of eigenvectors. They might only have one or two, especially if you restrict yourself just to the real numbers. Like maybe you don't care about complex eigenvalues, in which case you may not have any eigenvalue at all. By the way, can you guys think of an algorithm, a matrix that does not have a real eigenvalue? Yeah. Yeah, rotation matrices are a good example, right? If I take vectors, I rotate them 30 degrees, then it seems very unlikely I'm going to get a multiple of the same vector when I put it out, right? So clearly I'd have to introduce a complex component to do that. Does that make sense? An even simpler one, by the way, is just 0, 1, 1, 0. This is the matrix that just swaps the two elements, right? So if ax equals lambda x, oh, I'm sorry, actually that's completely dumb. No, ignore that example because x is an eigenvector of this thing, yeah? I'm sorry. Completely ignore that. I'm sorry. You're absolutely right. Rotation by like 90 degrees is a better example. Okay. Sorry for mumbling for a second there. All right, so let's get back on track. So, in general, we call our matrices non-defective, or a more positive, supportive way to put it is diagonalizable if we have a full set of eigenvectors, namely that they span Rn. Most matrices out there in the universe that we're going to care about in this course will satisfy this criterion for a very specific reason, which is that they're symmetric. We're going to come back to that in a moment. Just in general, by the way, I think we see this expression here a lot. Let's make sure that we understand why that's the case. So in other words, why does the word diagonalizable make sense, right? And this is a good review only because we've talked about LU factorization and QR. Remember, one of them involved row operations and the other potentially involved column operations. Let's think about exactly what this expression means. Ugh. So in particular, let's say that I have a full set of eigenvectors. Ugh. And moreover, I know that like AXI is equal to lambda I xi, like that. Okay? Then I can do our favorite trick where I'm just going to take all of my x's and combine them into one matrix. Like that, right? And of course, we know that this is the same as AX1, X2, AXN, like that. And now we can use the eigenvalue expression like this. This is lambda 1, x1, lambda 2, x2, lambda n, xn. Okay? Everybody with me so far? So, notice that this is just a rescaling of the columns of x, right? Each column gets scaled by a different lambda. That is a column operation. What side of the matrix do column operations go on? So we kind of know it's going to be multiplying by a diagonal matrix, right? What happens if I multiply like row the left side versus the right side by a diagonal matrix? Harry knows, but he's not going to answer. I get it. That's right. You got to multiply on the right. So this is x. Let's just call it. Let's be grown-ups here and call this big X times the diagonal matrix of lambda 1, lambda n. Does that make sense to everybody? So if I want to scale the columns by a set of values, then I got to put the diagonal guy on the right-hand side. Okay? And in particular, we call this thing big D. Okay? Now, is big D invertible? So I'd actually maybe let's think about it. So let's think of a good matrix that has a full set of eigenvectors. How about the matrix of all zeros? Yeah. So D is not invertible. Is X invertible if I assume I have a full set of eigenvectors? The answer is yes, right? Anytime I have a matrix with n linearly independent vectors as its columns, that's an invertible object. No? Mm-hmm. Is that true? Here's a diagonal matrix. Yeah. You guys are thinking too hard. Okay. Right, so we have to be a little careful. X is invertible, but D ain't. So in particular, I can write the following. D is equal to X inverse AX. Right? And so that's why people often say that a matrix with a full set of eigenvectors is diagonalizable. This is a term you hear a lot. Right? And the basic point is that if you conjugate it by the set of eigenvectors here, what you get left is a diagonal matrix. Notice everything I've done here is kosher. I didn't invert any non-invertible matrices. But you have to be a little careful when you do that. Does that make sense? Now, incidentally, oftentimes I hear people confuse that with X transpose AX. We'll see that those are often the same, but not always, right? So in particular, there's a class of matrices for which X inverse is equal to X transpose, which is the orthogonal matrices. And those are the ones we're often working with, okay? So in general, it would be kind of nice to be able to diagonalize a matrix. And in this course, we're going to mostly focus on algorithms that find eigenvectors of diagonalizable stuff. Like our proof of the QR division is going to depend very strongly on that. But there are matrices out there in the universe that are not, and for those you need some more specialized algorithms. In any event, there's a totally reasonable question you might ask, which is like, is there some condition I can put on A that guarantees that it's diagonalizable and is easy to check, right? Like it would be really annoying to have a chicken and egg problem, right? Like I want to know if a matrix is diagonalizable. The only way I can do it is to find all the eigenvectors. But if, you know, if that fails, I don't know if it's because my algorithm was bad or because it doesn't have the full set, right? We don't want to be in that situation. So in particular, right, that is our motivation for a very famous theorem from linear algebra. This is probably the last lecture in your course if you took a kind of theoretically oriented first year algebra course. If you didn't, that's okay, because we're going to cover it. The basic question that they ask is there a big class of matrices that is guaranteed to be non-defective? In other words, to have a full set of eigenvectors that span Rn? And the answer is yes. That class is the set of symmetric matrices. Sorry, I should be careful. That is a class. There can be other diagonalizable matrices, but this is certainly the most famous. Okay. Now, unfortunately, it is out of the scope of this course to prove the spectral theorem. Although it really isn't that hard. Now, to Chris's question earlier, that one really does require calculus. Only a little bit. Like you need at least that a function on a complex set that's continuous has an optimum. I think that's all you need. But at the very least, we're going to quote this theorem and use it a little bit. So in full generality, the spectral theorem actually says a little more than that, in fact. It says that even complex matrices that are Hermitian also have a full set of orthogonal eigenvectors. Okay? So if you remember, a Hermitian matrix is one that equals its conjugate transpose. So you take every element and you flip the sign in front of the imaginary part, and you transpose the matrix. Okay? Have we encountered Hermitian matrices before, just so I have some idea in this class? It's okay if you haven't. So about 50-50. Cool. So if you don't like thinking about Hermitian matrices and you prefer real value ones, that's perfectly fine. Hermitian is the symmetric of the complex world. Okay? So in your brain, every time you hear Hermitian, you can just think symmetric, and as long as you never care about a complex number, you're pretty much okay. Cool? Cool. Okay. However, we can actually prove a kind of handy little fact, which is that even if you have a Hermitian matrix with complex values in its entries, its eigenvectors have to be correspond to real eigenvalues. This one is easy enough to prove. We're going to kind of prove some like accoutrement around the spectral theorem, but we're not going to prove the spectral theorem itself. Oh man, I wish I weren't allergic to chalk. Okay. So, right. Let's prove this little lemma here. So in particular, let's say that A is a complex n by n matrix, and that we take an eigenvector. So Ax is equal to lambda x. But for now, x and lambda could both be complex valued. We don't know if they're real or not. Cool? All right. Moreover, we're going to assume, because we can always do this, that the norm of x is equal to 1. Is that the fire alarm or is that a truck? Sounds like a truck. Okay, so here's a fun trick we can do. Lambda, fun fact, is equal to lambda times 1. Any questions so far? Okay, but we have a very complicated expression for 1, which is this is the norm of x, right? So in particular, we can say this is lambda times the inner product of x and x. Incidentally, because we're in the complex numbers, I'll use this notation, which is sort of like the dot product with x and the conjugate of x, okay? So why do we do that? Well, we can move this lambda in here. This is equal to ax dot product with x, like that. Okay. And again, just by definition, this is really equal to ax transpose times the conjugate, like that. That's just the definition of dot products when you have complex numbers. Okay? So, any ideas? What should we do from here? Well, it's important not to think too hard, right? So in particular, we can take this transpose and extend it out, right? So this is equal to x transpose a transpose x bar, like that. And remember that if I take the conjugate of a conjugate, I get back the value I started with. So this is equal to a funny thing, which is x transpose a conjugate transpose x conjugate. Notice that these two bars kind of just cancel out. That's all that's happened here. I'm just making a really complicated expression. And why? Because this, well, what is a conjugate transpose if A is Hermitian? It's just A, yeah. This is x transpose AX conjugate, like that. Okay, so this is the inner product. Actually, no, let's keep writing it this way. Okay. But we know, because x is an eigenvector, this is x transpose times lambda x conjugate, like that. Yeah? But notice something fishy happened. Now I have a conjugate over this lambda, right? So this is really equal to lambda conjugate times x transpose x, like that. But this is just the norm of x again. We already know this is 1. So in effect, what did we just show? We showed that lambda is equal to lambda conjugate. And the only set of numbers for which that's the case are the real numbers. Okay, so lambda is in R. This is a nice fact about Hermitian matrices, is that they have all real eigenvalues. Cool? Okay. Moreover, if we have eigenvectors corresponding to distinct eigenvalues of Hermitian matrices, they must be orthogonal. This is a central result both in algebra and also in analysis. So you use this sort of infinite dimensional version of this to talk about PDE problems a lot, an elliptic PDE, if you're curious. So it's important not to think when you write these kinds of boring linear algebra proofs. So in particular, what do we do? Well, we're going to just take two eigenvectors with distinct eigenvalues and see if we can show that they're orthogonal, right? So let's say that we have ax equals lambda x, ay equal to mu y, and lambda not equal to mu, like that. That's our setup, right? Now, our previous result shows that lambda and mu are both real valued, right? That's what we just showed a minute ago. So now we're going to kind of basically do the same kind of proof again. So let's take lambda times x inner product y. Okay? So just like before, this is a x inner product y, like that. And because of essentially exactly this derivation here, this is the same as x inner product ay. In fact, there's a universe where the definition of Hermitian is actually here. It's not conjugate transpose. Okay? ay is equal to mu y, and mu is real, so this is mu x y, like that. Cool? Okay. I claim we're done. Why is this? So remember that lambda is not equal to mu. So I have two different scalars that are not equal to each other, but I multiply them by the inner product of x and y, and I get that they are equal to each other. So there's only one choice of this scalar value for which that can be the case, which is 0, right? So in particular, x inner product y is equal to 0, which is exactly what we wanted to show. Right? So we have orthogonal eigenvectors. So those are just some nice properties of Hermitian matrices. But the real nice property of Hermitian matrices that we like, which we are not going to prove here, is the spectral theorem. Here it is in its full glory. And essentially what it tells you is that if you have a Hermitian matrix, and by the way, if it's symmetric, that's good enough, then essentially it has exactly n orthonormal eigenvectors, possibly with repeated eigenvalues. So essentially what it's showing you is that like all Hermitian matrices, and in particular all symmetric matrices, are diagonalizable. Does that make sense? And moreover, they're orthonormal. By the way, notice that like we showed that if we have eigenvectors with different eigenvalues, they have to be orthogonal. I can always choose when my eigenvectors have the same eigenvalue to make them orthogonal, right? I can just orthogonalize them. That's perfectly fine. Cool? So this is a particular case where like, remember before we had this expression here, but now we know that the columns of x are orthonormal to one another, so x inverse and x transpose are the same. Yeah? Okay. So here's our full expression. I promise we're done with like linear algebra review. Any questions so far? Then we're going to talk about algorithms. Yeah. Oh, I sneakily covered it up so that if I made a mistake, you couldn't see it. Yeah.
So that line is we take conjugate out and we.
Which here?
Yeah.
This one.
Right.
From here. All this did was distribute the transpose, right? And then I'm saying that the conjugate of the conjugate is the same as the original value, right? So I put a conjugate on the outside, and then I had a conjugate the two things on the inside. Yeah. Mm-hmm. Yeah. Oh, sorry. Yeah. This line goes with that thing. Any other questions? Just a little bit of linear algebra review. It's important to remember when our problems are well posed. So in other words, what we've shown so far is we can diagonalize any symmetric matrix, and we can find at least one eigenvector of any asymmetric matrix. Okay. So here's going to be the question we'll answer for the rest of today, and probably some of the next lecture, which is the following. How do you find eigenvectors and eigenvalues in practice? So just out of curiosity, how'd you do it in linear algebra class? Do you remember? Yeah. Well, that is the definition of an eigenvector, but how did you do it on paper? Do you remember?
Oh, we did something with the determinant.
Yeah, so I think the typical algorithm in linear algebra class for computing eigenvectors looks something like the following. And then I'm going to ask you kind of a fun symbolic math question. By fun, I mean horrifying. So I believe what they typically teach in intro-level linear algebra, at least when I took it 1,000 years ago, was like, let's say that I want AV equals lambda V, as we say. Well, then in particular, we know that A minus lambda I times V is equal to 0, right? So that means that this matrix, A minus lambda I, must not be invertible, right? And an equivalent condition for not being invertible is to say that the determinant of A minus lambda I equals 0, if I found the correct lambda, right? And so I believe what you typically do, because your matrices are either 2 by 2 or 3 by 3 in college linear algebra class, is you take your A, you know, A11, A12, dot, 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 and then you start like subtracting lambdas down the diagonal, computing the determinant. I see smiles in the room because I'm sure you all suffer from this and have like hand injuries from having done it 1,000 times on paper. Or your iPad these days. I didn't have an iPad. I still don't have an iPad. Okay, so let's think algorithmically. Is this such a good idea? Like our first attempt might be to take this thing that we do in algebra class and translate it. Where are we going to run into trouble? We're going to run into trouble. Yes, big trouble. But oh, you mean big values? That's also true. There's a lot of multiplies. Yeah, you run into big trouble with big values. Yeah, here's a question. So you need to be able to evaluate the determinant as a function of lambda. Never mind, like, solve that this object is a polynomial, right? So on your homework, you actually worked out an algorithm for computing determinants. I believe all your late dates have passed, right? So spoiler alert, you can use LU factorization for that. Sorry if you got that wrong in your homework. Does that strategy work here? Not really, because you need to work it out as a function of lambda, right? So it's not obvious that you can do such a thing. So in fact, like basically converting this thing into this object, which is called the characteristic polynomial, is probably not the best strategy, at least for version 1 of your algorithm. Yeah? And so that's kind of annoying that basically you spend all this time in algebra class learning this strategy that really doesn't extend all that well beyond 3x3 matrices. Now, the reality is that if you go to like really fancy eigenvalue computation methods, occasionally there actually are cases where writing this polynomial down and solving it makes sense. But it's definitely not sort of version 1.0. In fact, by the way, this is a polynomial lambda. Doesn't look like it, but it is. But what is the degree? It's like probably n, right? Do we have a formula for, like, we know the quadratic equation for things that have, for 2x2 matrices, so we're good there. We can actually write just a formula for the eigenvalues of a 2x2 matrix. You can do it for 3x3. Can we do it for 6x6? No, right? Because we know that there's only formula for the roots of a polynomial up to what, degree 5, I believe? 4?
I think 5 is when it breaks down.
5 is when it breaks. Sorry, I was getting confused. Yeah. Cool. Do you know the history of the quadratic equation, by the way? It's kind of funny. There's like apparently like court mathematicians out there that would like challenge each other to duels. Yeah, and there was like some guy that figured out the quadratic equation and then would go around defeating all the mathematicians by challenging them to quickly solve quadratic equations. Sorry, where were we? Right, algebra. So in any event, we're back to the drawing board. Sadly for us, we learned a bunch of useless skill in college algebra class. So now we need actual algorithms that can do these things in practice. But here's the thing, and actually, going back to this fact that there exists no quintic equation, like, do we expect to be able to find the eigenvectors and eigenvalues of A in closed form? You know, like negative B plus or minus the square root of B squared minus 4AC. The answer is no. Like, in fact, there is no closed form expression for these things in a lot of cases. In fact, you can, an eviler professor than I would ask you on your homework to show that root finding and of polynomials and eigenvector computation are basically the same problem. So in any event, the best we can hope to do is approximate. That's my point. And somehow that's the idea that gets lost in college linear algebra class because we live in this happy universe where we can solve problems in closed form. Yeah? But in this class, we're all grown-ups, so that's not what we're going to do. We're going to approximate eigenvectors. We're going to do it fast. Okay? So in particular, here's our setup. We have an n by n symmetric matrix. So what do we know about A? Oh my gosh. It's full rank. Actually, that's not necessarily the case. Again, every time I ask you guys a question, the first counterexample I want you to try in your head is the matrix of all zeros. So A is not full rank, but it is diagonalizable. That's right, thanks to the special theorem. So it has a full set of eigenvectors x1 through xn, and a full set of eigenvalues lambda 1 to xn, so lambda n. In this lecture, we're going to sort our eigenvalues. So lambda 1, by convention, we'll think of as the biggest one. Yeah, God didn't make that the case. This is just a convention. Okay. In fact, probably halfway through the lecture, I'll forget and swap the order. Okay. And we're going to see why in like t minus 10 seconds. So here's going to be our trick. Essentially, what do we know about the eigenvectors of A? Well, we know that they span Rn. We can take any vector in Rn, and we can write it in this x1 to xn basis. Does that make sense? That's the nice thing it buys us. So if we take just an arbitrary v, we can write it in the following form. Again, this is only true for non-defective matrices. We don't like defective. So let's do a fun calculation. So let's say that I take v and I write it this way, right? So I say that v is equal to c1 x1 plus cn xn, where again, the xi has the property that a xi is equal to lambda I xi, like that. So what is a times v? Well, it's c1 a x1 plus cn a xn. And that's awfully convenient because we know like ax1 is equal to lambda 1 x1. So in particular, this is c1 lambda 1 x1 plus cn lambda n xn. What am I going to do? Let's multiply this thing by a again. I don't know. So let's a squared v. Well, it's a times this thing, right? It's a times this quantity. Yeah? So, in particular, it is c1 lambda 1 squared x1 plus cn lambda n squared xn. So, by our powers of induction combined, we can write, that's induction because I wrote dots. A to the k times x is equal to c1 lambda 1 to the k x1 plus cn lambda n to the k xn. Everybody agree with me? So essentially, every time I hit this matrix with A, all I'm doing is exponentiating the lambdas. Cool? Okay. So let's factor the tiniest bit. In fact, let's assume, by the way, that lambda 1 is non-zero, right? Otherwise, by the way, remember that lambda 1 is our biggest eigenvalue in magnitude. So if lambda 1 is 0, then like this whole problem is kind of boring. So in particular, how do I want to write this? Yeah. Lambda 1 to the k, let's factor out like that. We have c1 x1 plus, I'm going to write a second term here. So c2 lambda 2 over lambda 1 to the k x2 plus dot 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 plus cn lambda n over lambda 1 to the k xn. Just barely fit. Everybody agree with me? So essentially all I did was multiply and divide by this number. Okay, so what do we know about each one of these coefficients? Yeah, so remember that by definition, lambda 1 is the biggest eigenvalue, right? So lambda 2 over lambda 1 had better be in the range -1 to 1. And similarly for all of these things. Like that. Cool? Whew. So this is our observation so far. So let's assume for a minute that lambda 1 is unique. In other words, we don't have a repeated eigenvalue as our first one. That's actually a case that's not going to matter a ton. It turns out our algorithm will kind of still work, but I'll let you think about that at home. Then what is this thing approximately equal to? Well, you have one term that has like norm that's kind of staying around norm 1, and then you have a bunch of other terms that are decaying. So this becomes approximately equal to lambda 1 to the k c1 x1. Everybody with me so far? Because all the other terms here go to 0. Okay, this is exciting, right? So for large k, we have this funny expression. So how could I compute an eigenvalue? How could I approximate an eigenvalue in an eigenvector of a matrix? The dominant eigenvector, so the one corresponding to lambda 1. Well, I could take yes, Axel. Yeah, I can take an arbitrary vector v, literally just randomly generate it, multiply by a bunch of times, and now I get something that's parallel to x1, so I divide it by its norm and I'm done. Does that make sense? So this algorithm has a name. This is called power iteration. It looks like this. Vk is equal to a times vk minus 1, right? So vk is equal to a to the k times v0. And in particular, this thing converges to some multiple of the eigenvector. Now, is this a smart algorithm in practice? The way that I've written it on the board? Let's say my matrix is 1 by 1, and it is the number 2. Then what is going to be like v25? It's going to be 2 to the 25th times the thing I started with, right? So like notice that like this thing is very likely to explode numerically. Yeah? But at the end of the day, I just need something parallel to this, right? I don't actually have to keep it, right? So like in this case where lambda 1 has a modulus bigger than 1, this is probably not such an advisable technique. So here's my small edit to this algorithm, which is as follows. I compute W to be A times the previous thing, and then I just divide W by its norm. So notice now every single VK is unit length, right? And moreover, every single VK is parallel to A to the K times V0, right? That's easy to show. And so between those two, these basically converge to the same object. But this one is in a bounded norm space. That make sense? Notice, by the way, I've committed a cardinal sin in CS 205A, which is the class I taught 15 years ago. CS, whatever it is, 6S955. And what is the cardinal sin here? Well, I haven't told you which norm, right? Ooh, more than one cardinal sin. Yeah, right. I didn't put a subscript on that norm. That's because it actually kind of doesn't matter, right? We just need W to be bounded, right? And any of them will do that. In fact, there's a really clever choice of norm here, which I kind of like. But I'm going to put that here, which is the following. I guess I should swap these. That's fun. So let's say that I choose, I take our norm here to be the infinity norm. You guys remember what the infinity norm is? You suffered with it in your first homework. It's the thing that just takes the largest absolute value of a vector. Okay. Here's a fun little puzzler here. So in that case, let's look at A, V, K, like that. So in other words, WK, right? Or WK plus what, I guess. And look at its infinity norm. What does this thing converge to? So what do we know? We know in the limit, this thing is going to be like AV is like roughly lambda V, right? The previous iteration, the infinity norm of V is equal to 1, right? So in other words, what I get is that this just converges to the absolute value of lambda 1. There's kind of a sneaky normalization. So if you use infinity norm to normalize vector in this algorithm here, and you just look at the thing that you're dividing by, it will converge to the eigenvalue. Kind of tricky, huh? By the way, this is totally unnecessary. Like anything will work, but also it avoids taking a square root, right? It turns out this is kind of unnecessary here. Okay. So, any questions so far? Axel's got like an ambiguous, not quite question, elbow situation. Okay. Fantastic. So here's a problem. I've only given you one eigenvalue in my matrix. That's not what I set out to do. I mean, like at the end of the day, I'd like to compute more than one eigenvalue, and it's not obvious how to take this algorithm and extend it to more than one. Obviously, we're going to address that. There are a lot of problems out there in the universe, including many of the ones that we covered in the previous lecture, for which you only need one eigenvalue, right? So for example, some of those layout problems that we started with, we just wanted the dominant eigenvector, and we're done. All it takes is multiplying a bunch of times, right? Remember that the last problem we talked about in spectral embedding, we wanted to do the opposite of that, right? We wanted to compute the eigenvalue corresponding to, or the eigenvector corresponding to the smallest eigenvalue instead of the biggest. That, what was that?
Second smallest, right?
No, the eigenvalue corresponding. Oh,
Isn't it 0?
yeah, specifically for that one. But ignoring the 0 eigenvalue for a second, the one on the other end of the spectrum. How about that? Any ideas for how we could do that? Negative, yeah. So negative A is actually almost right. But remember that we converge to the dominant eigenvalue, but dominant here is up to sign. So taking negative A actually won't change that. But you're in the right church, wrong pew. What are we going to do? The inverse. That's absolutely right. So in particular, let's say that we have an eigenvector AV equals lambda V. For now, we're going to ignore the case where lambda equals 0. We're going to do that a lot today. Okay? Then, in particular, we have the following. Well, if we divide both sides by lambda and multiply both sides by A inverse, we get A inverse V is equal to 1 over lambda V. Yeah? So what does that show? That shows that this guy is an eigenvalue of A inverse. That make sense? We kind of already knew that, by the way. In the previous lecture, we had that formula for how to invert a matrix. Whew. OK, so remember what we did. We started by kind of defining lambda 1 is bigger than lambda 2. It's greater than s, is greater than or equal to lambda n. Let's assume they're all non-zero. What happens when we take reciprocals of positive numbers and inequalities? The order flips, right? So we have 1 over lambda 1 less than or equal to 1 over mod lambda 2. It's less than or equal to 1 over mod lambda n. Cool? So what happens if I do eigenvalue iteration on A inverse? Well, now the dominant eigenvalue is this one, right? So the eigenvector that I get is now on the other end of the spectrum of A. Does that make sense? Cool. So yeah, so here we have it. There's the eigenvalues of the inverse matrix. The largest magnitude one is now flipped. So this is a new algorithm. By the way, it's so funny when you read in your algebra textbooks, for some reason they give each of these little formulas a different name. This one's called inverse iteration for obvious reasons. OK. What is the complexity of this algorithm if I use, I don't know, Gaussian elimination for each iteration? This is a coded way of saying, what is the complexity of Gaussian elimination? Which is a thing you should be able to just, like every day you brush your teeth, you wake up, you turn around 3 times, these are big smells, big smells, big smells, and then you answer the complexity of Gaussian elimination. Yeah, it's cubic. So notice that our algorithm got kind of slow, right? One iteration of this technique suddenly takes cubic time. Or does it? We have to do a bunch of linear solves with a bunch of different right-hand sides. So what should we probably do to accelerate this? LU factorization. That's absolutely right. So we can make this algorithm faster by essentially factoring A equals LU once and then running this algorithm a bunch of times. And now every iteration takes quadratic time. Notice that the initial LU factorization still took cubic time, but at least I only had to pay for it once. Right? So this is a great case where LU factorization is a useful tool. Yes? In this case, K is kind of inductive. This is an algorithm you just iterate, and the more Ks you do, the closer you get to the eigenvector. Right? So you pick a number ahead of time, or there are a lot of different ways that you can do it. You could do that. That I would say is the typical solution of machine learning because they don't like to think about this stuff. Probably the better thing to do would be to look at the sequence of VKs that you get, and when they kind of stop changing, like look at the norm of the difference, for example, then maybe you stop. Right? We're going to actually try and formalize that in a moment. Great question. Any other? Cool. So we now can get the biggest eigenvalue. We can get the smallest eigenvalue. We're cooking with gas. Sadly for us, not all of our matrices are 2 by 2, so we're not quite done yet. We can also do something kind of sneaky. In general, let's say that I just choose some real number sigma. Right? Then obviously if AV equals lambda V, then A minus sigma IV, right, is equal to lambda minus sigma V. Yeah? So here's kind of a funny question. What is the dominant eigenvalue of A minus sigma I? Inverse. Sorry, I forgot that last little bit. So in particular, notice the following. So let's say that I did A minus sigma I inverse V. That's going to equal 1 over lambda minus sigma V, like that, right? We haven't done anything terribly profound yet in this lecture. So when is this value big? When do we get a big eigenvalue? Yeah, say it louder. Yeah, when lambda and sigma are really close, 1 over lambda minus sigma is really big, right? So actually the dominant eigenvalue of this guy is going to be whatever one is closest to, like you're going to choose the lambda that's closest to sigma, and that's the eigenvector that's going to dominate. Does that make sense? So this is a way to do a targeted search for an eigenvector, right? If I kind of know like there's an eigenvector out there with eigenvalue 7-ish, then I can compute this thing. By the way, there's and this also has a name. This is called shifted inverse iteration, in case you were wondering. Here's kind of a funny thing that you might worry about if you use this algorithm. I actually did, and then I went out there and read the research a bit, and I realized apparently this is actually not a concern, which is surprising. What happens if sigma is a really, really good estimate of an eigenvalue? Like hella good, so good. Well, what is like this value, 1 over lambda minus sigma? Yeah, it's like almost infinity, right? So this matrix somehow is actually quite ill-conditioned if you choose a good sigma, which totally feels wrong, right? Because your whole point here is to choose, a sigma that is close to an eigenvalue, right? There's like a really strange little contradiction there. It turns out if you do more careful analysis of conditioning than we did a few lectures ago, what you'll find is that the conditioning of this system is actually okay because you're looking specifically for this eigenvector. So like it's somehow the conditioning in that direction is all right, because it's not terribly sensitive. It's like blowing up that one thing that you wanted anyway, right? Which is kind of surprising. So anyway, I'll let you dig into the literature a bit to find that. But it is an obvious question, like, well, wait a second. Like this thing is totally ill-conditioned exactly in the case where I care about it. And it turns out this is actually just not a concern. So here's the sort of summary here. A minus sigma I inverse, that whole matrix, has the same eigenvectors as A, and the eigenvalues are these guys. They're 1 over lambda minus sigma, right? And so the only thing we have so far is one really boring algorithm, which is multiply a bunch of times. And that algorithm finds the biggest eigenvector of whatever thing you're multiplying by, right? So the trick here is that you choose sigma close to the lambda you're targeting. Then what you're going to get back is an eigenvector of A corresponding to the eigenvalue closest to sigma. The eigenvalue is different, right? The eigenvalue has changed, but the eigenvector is the same. Yeah. Sneaky, huh? Any other questions? I'm sorry. I'm rushing through this only because I think this is the easy part, and then suddenly it becomes really messy and hard. Like there's like no middle ground in this space. And I'm already low on time, so we're going to motivate QR algorithm and then maybe prove some stuff about it next time. Okay, so go back to, I think it was Axel's question. So let's say that we do this kind of algorithm, right? We do eigenvalue iteration. And I want to know like what k to choose. This is a totally reasonable question, right? What does the convergence rate of this thing look like? Like when do I expect this algorithm to very quickly reach an eigenvalue of A? Yeah, when lambda 2 is way smaller than lambda 1, right? Because in that case, that very first exponential term decays really, really quickly, right? And similarly, if lambda 1 and lambda 2 are close together, then it's going to take many iterations of this algorithm before I've damped out that second term a whole lot. Does that make sense, everybody? I mean, sadly for us, there's a chicken and egg problem because we don't know lambda 2. We can't evaluate that ahead of time. But that's sort of the intuition here. Cool. So we know the convergence rate of this thing is really good when the ratio between the first two eigenvalues is as good as possible. So here's a really sneaky trick. I could try to take a matrix and shift it. So in particular, this is kind of similar to our inverse iteration. Let's say that I continue inverse iteration. And now I look at AX, and now what I do is I look at maybe A, sorry, I'm like stuttering, minus sigma I, right? This thing has the same eigenvectors for any sigma. It's just the eigenvalues that change, right? So what am I to do? Well, in some sense, if I want my algorithm to converge really quickly, I might choose a sigma so that this ratio is really, really small. Does that make sense? So essentially, I might as well shift my matrix in such a way that my algorithm is going to converge really quickly. But of course, there's a problem, right? Which is, if I knew the best shift, I knew lambda 1, right? Because obviously the best lambda 1, the shift is lambda 1. Okay? So there's one more kind of basic eigenvector algorithm that we're going to cover here, which is a really sneaky thing. What we're going to do, which is kind of similar to the shifted iteration, is we're going to do one iteration of shifted stuff, and then we're going to just change sigma to be the better estimate of something close to our eigenvalue. Does that make sense? So in particular, let's say that V naught is approximately an eigenvector of A. Okay? So in other words, A V naught is like roughly lambda V naught. Not exactly, so this is not 0, but it's close. Okay? So here's what I'm going to do. I'm going to say, okay, I do my eigenvalue iteration. I get V naught, and it's not quite an eigenvector, but it's kind of close. And we're going to ask the question, like, what is the eigenvalue that is kind of closest to being the eigenvalue corresponding to V naught? Okay? It's kind of a funny problem. So we want to solve this least squares problem. Then over lambda of A V naught, do I have a minus? I do, minus lambda V naught. Okay, so what are we going to do? Our objective is squared, so we might as well expand it, because that's what we always do. So our objective is really equal to V naught transpose A V naught. Are you guys tired of doing this calculation yet? Because I feel like we do it every lecture. Minus 2 lambda V naught transpose A V naught, assuming A is symmetric, which is we'll do for now, plus lambda mod V naught squared, like that. So we're trying to minimize with respect to lambda. So in other words, we want 0 is equal to minus 2 V naught transpose A V naught plus lambda mod V naught squared, like that. Okay. So in particular, lambda squared, 2 lambda. I'm really bad at constants, I'm sorry. Okay, so in other words, we have lambda is equal to V naught transpose A V naught, at least when A is symmetric, over mod V naught squared. Cool? So what could we do? We do eigenvalue iteration for a while, and then we're going to update our lambda, and we're going to shift by this thing, and then we're going to keep going. Cool? So here's what this algorithm looks like. This has a name. It's called Rayleigh quotient iteration. There's a different way to derive it using the Rayleigh quotient. And essentially, here's what we're going to do. We're going to do one step of inverse iteration, right, where we're thinking of sigma as close as possible to an eigenvector of A, right? Then maybe we normalize just for yucks. And we choose the next sigma to be the best fit eigenvalue for our current estimate. Does it make sense? So this algorithm actually does converge, oftentimes much, much faster than for like a fixed sigma, which is kind of cool. It makes sense. In fact, I think you can show that in some cases this is quadratic and the other one's linear. Here's a problem, though. So in inverse, how do we make inverse iteration fast? What did we do? We did LU factorization, right? We took our matrix, we prefactored it as LU, and then we could do blazingly fast iterations. Can we do that here? No, right? Because the matrix that we have to invert in every step is different. We change sigma all the time. So now, every iteration of this thing takes cubic time. So notice that you need to save like on the order of n iterations of inverse iteration with a fixed matrix in order for this thing to be valuable. There's actually a bit of a toss-up when you look at efficiency per iteration versus the number you have to take, which is kind of an interesting trade-off. If you read the analysis, by the way, in a classical linear algebra textbook, they often omit this, which is kind of funny, because they think of conversion rate as like a function of k, which is absolutely right. But for each k, the amount of computation you have to do is a lot bigger in this technique. Does that make sense? Of course, there are ways around that, like maybe you find some sneaky ways to like approximate the matrix inverse and so on. You can do this all day, but at least the basic technique is not so clear. Okay. So hopefully I've convinced you that like, if we want to do like a targeted search and destroy mission to find a single eigenvector of a matrix, we totally can, right? There's like a bunch of algorithms out there, and they're all basically variations on the same theme, which is just multiply a bunch of times, okay? Sadly for us, sometimes we want more than one eigenvector for a matrix, and it's not obvious what to do. I mean, like, I guess you could like take this algorithm and initialize it with a bunch of different sigmas and kind of like, you know, pray, or like use one of those clever formulas that gives you the distribution of eigenvalues. But that turns out not to work terribly well. So instead, now for the rest of this lecture, and I guess the beginning of the next one, we're going to motivate techniques that find more than one eigenvalue at a time, or at least the eigenvalues in sequence. So to motivate that, here's kind of a sneaky question. So, oh, good. It's like there's intelligent design, but the reality is I just didn't erase this board. So if we look at AKX here, like this, and remember that I said randomly choose x1, right? Like just choose some x and don't worry about it a whole lot. Let's say I had really, really bad luck. Like so bad luck, hella bad luck. And in particular, I chose x so that x1 is equal to 0. Which could happen, right? Or sorry, at least c1, I guess, is equal to 0. In other words, the projection onto the first eigenvector just happens to be 0. I chose something that was orthogonal to it. The probability of doing that is 0, but like maybe I'm in like some terrible universe and I just had bad luck. Does that make sense? So remember, again, we initialize with a randomly generated x, but in this really bad case where x happens to be parallel to the orthogonal space to x1, then no matter how many times I multiply by a, what is this first term? Paul knows the answer. He's just being shy. 0. Yeah? Because if I multiply 0 by anything, I just get 0 again. So in that really bad luck case, what does my algorithm converge to? Well, it just converges to lambda 2, right? You get the second biggest thing. Of course, this doesn't happen in reality because like you're just very unlikely to choose that bad initial guess. But we can leverage that fact to target more than one eigenvector. And here's a possible algorithm that we could do. This is not the world's most efficient technique, but it's certainly version 0.0, which is as follows. I could compute the dominant eigenvector x0 by power iteration. So I guess that should be x1. Now I'm going to project that out of my initial condition for power iteration. I'm just going to run the whole algorithm again. And now I'm going to get x1. Project that thing out, run the whole algorithm again, and I should get x2. Yeah? At least mathematically, that should work. Let's think algorithmically. Like, is that such a good idea? No. Why, Harry? Because I wouldn't ask it otherwise. Thank you for that useful answer. Yes, Axel. Yeah, Axel makes a great point. We don't actually get to compute eigenvectors. We just get to compute things that are close to eigenvectors, right? And so what happens, I project x0 out of v0. Well, sadly for me, there's still maybe a tiny bit left of that first eigenvector in v0. So I run eigenvector iteration again, and the first thing it wants to do is amplify that little tiny bit. Before I know it, I'm back to where I started. Yeah, so that's not so good. But this algorithm can be kind of adapted in some ways that make it a little more practical. Does that make sense? So this is going to be our strategy for computing eigenvectors. We're going to do it in two different ways. First, we're going to kind of do it successively, like first compute the dominant one, then the second dominant one, then the third one. And then we'll talk about a technique that is on the other side of the spectrum. It computes the whole thing. There's more complicated methods out there called Rayleigh-Ritz methods and so on that compute like k eigenvectors on the two ends of the spectrum simultaneously. There are all kinds of weird algorithms out there for eigenvectors. We are not going to cover that. We're just going to cover the case where you only want a few and the case where you want them all. Okay, so and throughout this lecture, and basically until the end of time, we're going to assume our matrices are not defective. Okay. So here's a kind of sneaky thing that we can do, which is the following. So sorry, I'm going to turn pages in my notes here. So let's say that I've computed some set of eigenvectors. Here's the thing that I can do. Let's say that I construct a matrix P, where P projects out the first k eigenvectors. P v1 to vk. Okay? Where these are eigenvectors. Okay? So now, what are the eigenvectors of AP? Well, I claim that they're actually the same as the eigenvectors of A, right? So in particular, let's say that I have vi. Well, I have two cases, right? So we know that this is equal to, what is p vi if I is less than or equal to k? It projects stuff out, right? So it's just 0, right? So it's A times 0, like that, if I is less than or equal to k. And what happens if I project out this thing and I'm orthogonal to that space? well, then I haven't done anything, right? So vi if I is bigger than k. Does that make sense? So if p projects out the first couple eigenvectors and they're all orthogonal to one another, then we have these two cases. But notice, of course, this is the same as lambda I vi, right? So this is equal to vi times 0 if I is less than or equal to k, lambda I if I is greater than k. So what we've essentially shown is that this matrix has a full set of orthogonal eigenvalues, eigenvectors, and all I've done is essentially I've taken some of the really big eigenvalues and I've replaced them with 0. Does that make sense? So notice, what is the dominant eigenvector of AP? Yeah, it's actually lambda, I guess, k plus 1. Yeah. So what I can do is eigenvalue iteration on this thing, which notice that's like almost this algorithm here. That like essentially, in this algorithm, we project it once and then do eigenvalue iteration. All I'm suggesting here is to just keep projecting it in every step. And this thing is much more stable. Does that make sense? Yes, Axel. That's right. Yeah, so I essentially multiply by A, and then I project out. And then I multiply by A, and then I project out, right? Yeah, which in principle should be the same as this algorithm. But in practice is much more stable, because now I just keep zeroing out the component that I don't like. Yeah. OK, so this is an example of a sort of generic strategy, where essentially this is something called deflation, which is a cute term, which basically says I'm going to take my matrix A, I'm going to compute a few eigenvalues or eigenvectors, and I'm going to do something to A to kind of reshuffle the eigenvalues to expose ones that I haven't seen yet, right? And essentially there's a generic strategy, which is typically to compute this thing, the conjugate of A by a matrix P, where maybe P projects out stuff. That's going to be our strategy. Incidentally, you can convince yourself that pre-multiplying by P transpose, in this case we did here, also doesn't do anything. I'll let you think about that at home. OK, so a more generic version of this strategy uses the following fact. Let's say that A and B are similar, meaning that there exists a T, so that B is equal to T inverse A times T. Then I claim that they have the same eigenvalues. And moreover, you can get the eigenvectors from each other quite easily. Any idea how to do this? Well, since we're a little low on time, I'll let you prove this one at home. Really, the proof is extremely straightforward. You just say, like, take an eigenvalue, an eigenvector of B, so Bx is equal to Ax, right? What was that? I guess if you use the projection for a very specific choice of T, but more generically speaking, it's just absolutely true. You can conjugate with any invertible matrix like this, and you don't affect the eigenvalues. Okay. Essentially, like the eigenvalues of one of these are going to be like T times eigenvalues of the other ones, or something like that. Okay. Eigenvectors, rather. So, essentially, what does that mean? This like reveals to us some like sneaky ways to mess around with our matrices by essentially just like reshuffling them by applying these kinds of transformations, and we know that's not going to affect the eigenvalues, so that's perfectly kosher. Okay? So in fact, here's a really fun strategy. I love this strategy because it synthesizes. We like to synthesize in this class. Okay? My phone keeps ringing. I don't know what that's about. So let's say we're just going to do the first iteration of this algorithm. And in particular, let's say that we compute x1. So we know A x1 is equal to lambda 1 x1. We just do power iteration, and we find that fact. Okay? Now we're going to do a really sneaky thing. Remember from our lecture on QR factorization, this is kind of an unexpected twist, that I can choose a matrix H. Remember what H stands for? What was that? Householder, right? I'm going to choose an H with the following property, that H times x1 is equal to E1. Remember that was our first step of QR factorization using the stabilized algorithm? So here's a really bizarre thing. Let's say that I take H, A, H transpose, and I multiply it by E1. So first of all, by the way, if I take any vector orthogonal to E1, notice that it like kind of just leaves it alone. But in any event, what is this thing? Any idea? Well, H transpose times E1 is just X1, right? Because remember that H is orthogonal, so that's why I get that. So in particular, this is HA times X1, but X1 is an eigenvector of A, so we know that this is lambda 1 times HX1, like that. What's HX1? What's E1? So what did I just show? E1 is now an eigenvector of this matrix with eigenvalue lambda 1. So all I've done is kind of reshuffle the eigenvalues a little bit. Everybody cool so far? This like feels kind of arbitrary. It's a really sneaky trick. This is not one I would have thought of had I not found it in someone's book. Okay, so now for my next trick, I'm going to do the following. So what is H times A times H transpose? Sorry. Well, just as a matrix. Well, this expression here essentially worked out its first column, right? Remember, if I take a matrix, I multiply it by E1, I'm extracting the first column of our matrix. So we know that it's lambda 1 E1. So in other words, it's like lambda 1 and a bunch of zeros. Cool? Then we have something here. It actually doesn't matter what it is. And something here. So my matrix looks like this. We don't know anything, but we're going to give the name of this n minus 1 by n minus 1 submatrix. We'll call it B. Everybody with me so far? What are the eigenvalues of B? Well, for one, at least for this matrix here, remember this has the same eigenvalues as A, right? So this entire big matrix has the same eigenvalues of A. Moreover, let's say for now that A is a symmetric matrix. So it has a perpendicular set of eigenvectors. What do we know about all the eigenvectors of HA, H transpose? Well, they have to be orthogonal to E1 because we already showed that E1 is an eigenvector, right? So in particular, they just live in this lower block here. So in particular, what we've shown is the eigenvalues of B are equal to lambda 2, lambda n. Isn't this cool? Do you see what just happened? I get really excited about this algorithm. I think it's really clever. Like, this is so sneaky. Do you see what? This is so cool. So essentially, you started with the matrix A. You found its first eigenvector. You construct the householder reflection, this weird thing that we drew in the previous lecture, and you conjugate it with it because reasons. And what comes out is this matrix where the lower n minus 1 by n minus 1 submatrix has all the remaining eigenvalues. So notice this gives us a really clever algorithm for computing eigenvalues. I compute lambda 1, and then I deflate by conjugating with H. I extract this lower submatrix. I compute the principal eigenvector of this thing. That gives me lambda 2. I deflate this guy. And I keep going. And notice every time I do that, my algorithm gets a little bit faster, right? Because I'm working with a smaller matrix. Yes?
Would you say this is a algorithm?
Ah, great question. What is this called? This is called householder asymmetric deflation. So it works even when A is not symmetric, it turns out. Because it actually doesn't matter what's in this upper block here. It's obviously 0 if A is symmetric. Okay, so this is the basic trick that what you do is you conjugate with H. You know that lambda 1 ends up in the upper corner, and then what's left in B is going to be the remainder. So you recursively call your algorithm, which would be a terrible way to code it. And you keep going. Cool? And then yeah. All right. Well, conveniently, we've reached the end of our lecture. So what we're going to think about next lecture is what if I want all the eigenvalues of A? Like I'm greedy. So like the previous algorithm is still like not terribly fast, right? Because I have to compute one by a bunch of multiplies and then the second one and so on. So if n is pretty big, like this is clearly not a very efficient or parallelizable method. So the next algorithm we're going to do is going to be really, really sneaky. In particular, notice that, by the way, the reason that we chose, one of the reasons that we like the householder matrix is because we want to conjugate with the inverse here, but inverse and transpose are the same. A question we might ask is where else could we find a useful orthogonal matrix? And just for a small clue, let's say that I factor A equals QR. from the previous lecture? Well, there's only one orthogonal matrix that's somehow built into A that we know about in this class, which is Q. So let's do the following. What is Q transpose A Q? Well, that's Q transpose Q R Q. What is Q transpose Q? Identity for square matrix. So this is RQ. This is going to lead us to the most elegant, beautiful algorithm in all numerical algorithms, which is the following. I take A, I factor it as QR, and then I replace it with RQ. Because that's the only orthogonal matrix I can think of conjugating with, right? This leaves the eigenvectors alone, or eigenvalues rather. And it turns out this thing is going to converge. It's going to converge to a diagonal matrix of eigenvalues. Totally not obvious from this form. So we're going to spend probably a large piece of our next lecture justifying this really sneaky trick. And this is like 2 lines of code in MATLAB to get all of the eigenvalues you could possibly want. Okay? So with that, everybody have a lovely Tuesday. Please start your homework, and I will see you on Thursday.